Now remember at the beginning of the semester we talked about this interstellar visitor called Oumuamua. Now why we said it looks like a alien spaceship? So from scientific observation they believe is fluid inside this aircraft carrier size object, and it looks like it's doing a gravitational slingshot on our sun and is rotating, so it will create artificial gravity. We discussed it too. And then it seems from observation its trajectory is not entirely due to gravity. It also is has thrust, modify its trajectory. So this all unusual property makes some professor says there is a possibility this is an alien spaceship. Well, we don't know yet, do we? Now we can move to higher dimension elastic condition. For condition in 2 dimensions, you would have 3 equations. Kinetic energy conservation, you have 1 equation. Now condition in 2 dimensions, you have momentum in x direction conserved. Momentum in y direction conserved. So you have 3 equations in total. So this is one example. If you have 2 cars collide, so the momentum in x direction would equals to this initial momentum. Momentum in y direction after this condition would equals to initial momentum in y direction. And this is a more advanced problem for binary ball condition. Now, after the condition momentum of this black ball and this white ball, they should add up to momentum of white ball before the condition. It's just the math. And in 3D case, you're going to have 4 equations because you have 1 kinetic energy conservation, and then you have 3 momentum conservation equations. X direction, momentum conserved. Y direction, momentum conserved. Z direction, momentum conserved. So basically that summarizes this chapter. So you have an impulse momentum theorem. Total impulse equals change of momentum. Then you have, with impulse approximation, you have conservation of momentum. And then for condition, which means you need to safely disconnect external impulse. Then you always have momentum conservation. Now for momentum, you have elastic condition or inelastic condition. Depends on where the kinetic energy is conserved. Then you have complete inelastic condition. Those 2 objects stuck together. Okay, now let's quickly talk about center of mass approach of a system. So if you put M1 at orange M2 here, then center of mass of the system should be calculated like this. Now if you choose your zero, your origin to be in the middle of M1, M2, then you can write down your center of mass coordinate. the center of coordinate to be this. Now, we prefer this kind of coordinate system because we have M1, M2 symmetric, so you can have center of mass of the system is right as this. Now, if you have more than two objects, it's just that this equation gives you center of mass location of the system in the x direction, and you can generalize it to y direction and z direction. Just you always use this one, the total mass m1 times x coordinate of m1, m2 times x coordinate of m2, and so on. This will give you the center of mass coordinate of the system. Now, if we use the fact our Earth is here, the Moon is here, we try to draw this picture on scale. So there's the size of the Earth and the Moon is here. So you can imagine where would be the center of mass of Earth-Moon system? Is it inside Earth or somewhere in between here or here or outside? Now we plug in all the numbers, we use the equation, we find actually the center of mass system of Earth-Moon system is inside the Earth. Now, if you have a continuous distribution object, you have to integration. And sometimes center mass of the object can be outside of this object itself. For example, this ruler, the center of mass should be somewhere here, outside of this ruler. Now, then we can apply Newton's second law to be a system of particles. Now, if you have system particles, then the center of mass acceleration of the system only depends on the net external force. You don't need to worry about the internal force for the center of mass acceleration of the system. And this is one example. You have a projectile launched, and at here it explodes, and have one piece dropped here, last piece dropped here. So during the explosion, you only have the internal force, which means it won't change the center of mass velocity of the system, so the center of mass of the system will still follow this projectile trajectory to here. So you can predict where the center of mass of the system would be even if it explodes. Now, which means if you find this piece, you know the center of mass location, you can calculate where the other piece should be. So you use the formula for center of mass coordinate to find out where the location of this piece to be. Now, if you have more than one particle, the total momentum of the system is momentum of each particle add up together. So if the net external force on the system is 0, the total momentum of the system should be 0. Yeah, so we have quickly go over the chapter momentum and kinetic. And there are some other examples, workout examples on this example video. Hope you can check those videos too to have a better understanding of this chapter.